The topic for today is going to be Eulers Method. And so let's think about this for a second and build up to this Eulers Method thing. So how do you evaluate a function at a given point? Well, it's fairly simple. If you have f of x is equal to x squared plus 2, and we want to find the value of the function when x is 3, that would equal 3 squared plus 2, which is 11. So you're just simply substituting this value into your function, which is very nice if you have a function. Now, how do you evaluate a function at a given point if you know the derivative and a point on the function? So what we have is this differential equation here with the initial condition of 3, 0, and we want to evaluate this function when f is 1. Well, first thing is we do not know the function, so we are going to have to separate our variables, integrate, and get the original equation from this. Separating your variables, it's going to give you y dy equals negative x dx, and then we're going to integrate both sides of our equation, which will give us y squared over 2 equals negative x squared over 2 plus c. We'll use the initial condition to find out what c is, plugging 0 in for y and plugging 3 in for x. So that's going to give us c is equal to 9 over 2. All right, so we can substitute this back in, giving us y squared over 2 equals negative x squared over 2 plus 9 over 2. We could go ahead and multiply this whole equation by 2 to get rid of our fractions. That will give us y squared is equal to negative x squared plus 9. All right, so now we want to evaluate this function when x is 1. So that's going to give us y squared is equal to negative 1 plus 9. And then negative 1 plus 9 is 8, so y squared is equal to 8, giving us y is equal to positive or negative square root of 8. All right, so that's how you would find the value of a function if we are given the derivative of that function. All right, so on the previous problem, we were able to separate the variables and integrate and actually find out what the original equation was. However, how do we evaluate a function at a given point if we know the derivative and a point on the function? However, it is going to be impossible, at least with the methods that we know, how to analytically calculate the antiderivative. All right, so if we have this particular differential equation here, you cannot separate the variables on this, because if you move the y's over to this side, that would give you 2y plus dy. And in order to solve by separation of variables, it would need to be 2y times dy. So we cannot solve this differential equation by separation of variables. So we're kind of stuck. We run into a problem. So differential equations will give you the slope dy dx, and they will give us an initial condition, which is a point on that function. You can easily write the equation of a tangent line from this information, because a tangent line, you need a point and you need a slope, both of which will be given to you. And then we can use this tangent line to approximate any value on that function. The problem with this method is that it is only reasonable for approximating values close to the point of tangency. Further away from the point of tangency, we get further off on our approximation. So for example, if we know that our graph looks like this, and we have the slope of a tangent line here, and we got the equation of this tangent line, I can use that tangent line to approximate any value on the function that I want. Well, as long as I stick close to that point of tangency, that difference between the approximated value and the actual value is pretty close. It's a small difference. But if I wanted to approximate the value of the function way out here, that's going to be way off because my tangent line would be way up here. And that's going to be a very big difference in the approximation. So this tangent line can be used to approximate any point on your function. However, it is really only close to accurate as long as we stay close to this point of tangency. Since not all differential equations can be solved, it is often necessary to approximate our solution. There are several ways of doing this. The method that you will need to know for the AP exam is called Eulers Method, and this is the method that this video is going to be covering. We have done linear approximations using tangent lines before. So let's take this parabola right here, and we have the differential equation dy dx is equal to 2x plus 1 with the initial condition 1, -3. And the question says use the tangent line to approximate f of 1.1. Well, the point of tangency is at x equals 1, and we're approximating the value of the function at 1.1. So that's pretty close to this point of tangency, so it should be fairly accurate. All right, so let's go through this process. In order to get the equation of the tangent line, first thing I need to know is what is the slope of my tangent line, which is dy dx, and that would equal 2 times 1 plus 1, which is 3. So the equation of our tangent line will be y plus 3, which is from the y value of the point, equals the slope of our tangent line, which is 3, and that is from this value right here, times x minus 1. All right, so if I go ahead and solve for x here, or solve for y, this would give me 3x minus 3, so y is equal to 3x minus 6. If I want to approximate this value, then that would be 3 times 1.1 minus 6, which would be 3.3 minus 6, which is 2.7. All right, so, and it's a negative 2.7, sorry. And so if we look at this function right here, when x is 1, the actual value is -3, so we're approximating 1.1 to be -2.7, which is a fairly good approximation for this. So now let's start this process with a differential equation we can solve so that we can see how this works. Given dy dx is equal to 2x minus 6 with the initial condition for 3, what is the value of f of 5? All right, so going through the same process we did on the previous problem. The first thing we want to get is the equation of the tangent line. All right, so that means dy dx is going to be 2 times 4, which is our x value, minus 6, which comes out to 2. So the tangent line will be y minus 3 equals 2 times x minus 4. So we got 2x minus 8 and 2x minus 5. That is our tangent line. We're going to use that tangent line to approximate f of 5. So that means we're going to evaluate when x is 5, and that's going to give us 10. Let's go ahead and write it all in. 2 times 5 minus 5, just 10 minus 5, or in other words, 5. All right, so what we're doing is saying when x is 5, the point on the tangent line has a y value of 5. Now the actual value of the function when x is 5 is 3. We used a tangent line to approximate the value on this function. Now, instead of using the tangent line to calculate f of 5, what if we recalculate the tangent line to get a new equation of a tangent line, and then use the new equation to calculate f of 5? All right, so looking at this blue line is our tangent line from the previous slide, and we know that if we had followed it, the tangent line was going like this, and we found that the approximation came out to 5. Now, the problem is that's pretty big discrepancy here in the accuracy. All right, so what we want is a better way of approximating the value of the function. And so what we're going to use is we're going to take that tangent line and halfway through, or halfway to 5, which means at 4.5, we're going to recalculate a new tangent line based upon this point. And then that'll give us a new tangent line equation. It's not really tangent, but if that point was on there, it would be. And we're going to use this new tangent line equation to approximate the value of the function. All right, so that's kind of the process that we are going to use. All right, so let's go ahead and find the approximation here. All right, so I went ahead and worked this out. 2x minus 5, y equals 2x minus 5 was the equation of our tangent line from the previous slide here. We know that dy dx is equal to 2x minus 6 from the previous slide. And we know that the point here, if you plug 4.5 into that tangent line, when x is 4.5, the y value is at 4. All right, so we now know the coordinate for this point. We can use dy dx to find out what the slope of our tangent line is at x equals 4.5, and that comes out to be a slope of 3 for that tangent line. So we now have a slope of 3 and the point that is on that line. So we can use that information to calculate the equation or write the equation for that new tangent line. Well, we now will use that equation of a tangent line, which is our green line, and we're going to use it to evaluate what the function is when x is 5. So you plug in 5, you get 3 times 5 minus 9.5, which is 5.5. Now, if you remember on the previous slide, our approximation came out to 5 when we used this blue tangent line. So when we used the blue tangent line, the graph went right here. And that was not particularly accurate, so what we did is we broke up this tangent line and we recalculated it halfway from the point of tangency to the value that we want to evaluate at. So the point of tangency was at 4. We wanted to evaluate when x is 5. So halfway through, we recalculated the tangent line. And then we used this new tangent line to approximate that point. And it came out to be 5.5. So that was more accurate than our original tangent line. So this process could be repeated at smaller intervals to give us an even closer approximation. This process could be repeated at smaller intervals to give us an even closer approximation. So it's kind of like our Riemann sums. You can do one rectangle to get an approximation of an area, but if you use 50 rectangles, you're going to get a better approximation. Same concept with Euler's method. You can use a tangent line to get an approximation of a value on a function, but if you calculate using multiple tangent lines, those tangent lines are going to bend around and become more accurate. All right, so given this example where dy dx is equal to 3x minus 2y with initial condition of 1, 3, we want to approximate f of 2 using Euler's method with 2 equal subintervals. All right, so the first thing we want to do is we want to find out what is the slope of our tangent line. So dy dx evaluated at 1, 3 would give us 3 times 1 minus 2 times 3, which is negative 3. That's the slope of our tangent line. All right, so we want to use this information here and here to get an equation of that tangent line. So that's going to be y minus 3 equals negative 3 times x minus 1. Or negative 3x plus 3, which gives you negative 3x plus 6. That would be the equation of our tangent line at 1, 3. Now, when x is 1, that's fine. Or if I want to approximate the value of the function close to 1, like 1.1 or 1.2, this tangent line would be okay, and it would give us a close approximation. However, we want to approximate the value of f of 2. So this really probably won't give us a very good approximation. Not as good as if we recalculate a new tangent line. All right, so what we're going to do then is we're going to say, what about if we use we're going to calculate this halfway from 1 to 2. Halfway from here to what we want to figure it out. So halfway would be 1.5. Well, using our tangent line, that would be -3 times 1.5 plus 6, which is 1.5. All right, so this would be the coordinate for the new point of tangency. And dy dx at this point would be 3 times 1.5 minus 2 times 1.5, which is 4.5 minus 3, which is 1.5. Okay, so that will give us the equation y minus 1.5 equals 1.5 x minus 1.5. Distributing. Adding 1.5 to here is going to give you negative 0.75. And we want to now calculate the value of the function when x is 2. So that's going to give you 1.5 times 2, which is 3, minus 0.75. And that gives us an approximation of 2.25. Okay, and you can see right here, if we zoom in, we may not be able to zoom in on this, but if you will look at this graph right here, when x is 2, the value of the function we approximated was 2.25, which would be about right here. All right, so putting a point right there, that is approximately the value of the function. And if you notice, you can see these horizontal tangent lines, which tell us that our graph is going to be having a minimum based on the curvature here. So I'm looking at this thinking my graph is probably coming down here somewhere and then curving and going up towards this direction. And so 2.25, yes, that does give us a close approximation of the value of the function when x is 2. All right, I'm going to go ahead and take a look at the same question, and we're going to reduce this process because it's kind of a long process, and we get 2 tangent lines. You can do even more tangent lines, and it becomes more complicated. We're going to reduce this process down to filling in a table. Since we're approximating f of 2, and we are starting with x equals 1 using 2 equal intervals, delta x, which is your change in x, must equal 0.5. So we're going up by halves because we're doing 2 equal subintervals, starting with x equals 1, going to x equals 2. So that means our x value is going to go from 1, and then 1.5, and then 2. All right, so that gives us 2 equal intervals. Now this table that we're going to build, this is how I would like for you to work these out for your AP test. Make 4 columns on this table. The first column is going to be X. The second column is going to be Y. The third column is going to be Y prime delta X. And then the last column is going to be Y plus Y prime delta X. Now, where do these things come from? They come simply from the equation of a line. The equation of a line in point-slope form is y minus y1 equals m, x minus x1. So, therefore, m is your slope, which we know from calculus is dy dx. I'm going to write dy dx as y prime using that notation. Well, if you take two x values and you subtract them, what you are finding is the difference between, or the change in those x values. So we're going to call that delta x. So what this gives us now is y prime delta x. And we're going to take this y value and we're going to add it over to the other side. So we now have y prime delta x plus y, or in other words, y plus y prime delta x. So when you see this, this is going to be simply your equation of a line, and we're just filling in the values. All right, so we started with 1, 3 as our initial condition. Y prime, well, we used what dy dx was to calculate y prime. So that was 3 times the x value minus 2 times the y value. Delta x is going to be the same for all of these. Delta x is what we're changing in x here. These are going by 0.5s. Okay? If we were doing 4 subintervals, then delta x would have been 0.25. If we were doing 10 subintervals, we would go delta x would be 0.1. All right, so then this is y prime, this is delta x, multiply those things together, gives you this. And now we have y plus y prime delta x. Well, y prime delta x is the value we had right here. So we just bring that over. The y value is the y value from your table, which is 3. So bring that over. Add those two things together, and that gives you 1.5. This is your new y value, because if you look at this equation up here, we just found y prime delta x plus y, and that gives us our new y value. So this value comes over here, and then we repeat the process right here. All right, so dy dx is still 3x minus 2y, but we calculate this using these x values and y values instead of the original ones. 0.5 was our delta x. Working this out, you get 0.75. 0.75 is our y prime delta x. So the y value of 1.5 comes from here. Add that to 0.75 and you get 2.25, which becomes our new y value. And that also is the approximation when x is 2. If I wanted to know what's the approximation of f of 3, then I would just keep extending this process. The next x value would be 2.5 and then 3. Now, this problem was going by 0.5s because that was determined right here. 2 equal subintervals, and we started with 1 and we were going to 2. So 2 subintervals would put us at 0.5 for each of those. All right, so let's take this problem here. Given dy dx is equal to y with the initial condition of 0, 1, approximate f of 2 using Euler's method with 4 equal subintervals. All right, so 4 subintervals. Let's go ahead and make our table right here. The first column is x. The next column is y. And then we have y prime times delta x. And then we have y plus y prime delta x. All right, so the initial condition is 0, 1. Y prime, well, we know from up here, y prime is y. So y prime, that's going to be 1. That's our y value from right here. Now let's think, delta x. If we're starting with an x value of 0 and we're going to an x value of 2 with 4 equal subintervals, that means that we're going to have to go by halves. So this would be 0.5, 1, 1.5, and then 2. We can go ahead and fill those in. Now delta x is going to be 0.5 for everything in this problem. So you have 1 times 0.5, which is going to be 0.5. Then we have 1 plus 0.5, which is 1.5. That becomes the new y value. So now y prime, well, we know y prime is dy dx is equal to y, so 1.5 is our new slope. Delta x is still 0.5. If you multiply those together, you're going to get 0.75. So now we have 1.5 plus 0.75, which is 2.25. That becomes our new y value. I'm going to fill this table in here, and so I'm going to pause the video, fill it in, and then you can follow through with the rest of that. All right, so we can see from this process that we come out with an approximation of 5.90625, which is going to be way more accurate than using just one tangent line, or even for that matter, 2 tangent lines. All right, I'm going to go ahead and stop this video right here, and there will be a part 2 to this video, so you can catch that to get the rest of the notes and examples. And there's some really good information on that second part, so really do not skip over that.